Well, that was certainly interesting. We had a little bit of technical difficulties there with the intro, but I want to thank you very much for joining us today on this webinar. Uh, with every webinar, I'm sure that you've been in, you'll know that you will be muted for the presentation. However, if you do want to ask a question, feel free to do so via the chat, and we will be looking at those questions at the end of the presentation where we can go over those specific that you may have. Or if you would like some more detailed information, possibly a little bit more personalized or catered demonstration for your specific need, feel free to include that in the chat as well, and we will be happy to contact you and set that up to do it. So let's go ahead and get started. My name is David Cash. I'm a member of the marketing team here at Mountz. I've been with the company for over 16 years now, and it's been a very great and fantastic place to be employed and be a part of. Our company itself was founded in 1965. We do have three different locations. We have our corporate office in Western Service Center located in San Jose, California. We have our distribution warehouse and our Eastern Service Center in Foley, Alabama. And we also have our international sales and service in just outside of London, England. So those are our locations. We have or excuse me, we're the first company to develop the electronic torque analyzer. We did that for the military in the 70s. And since then, we've had 18 different iterations of torque analyzers. And we have some really good things on the horizon coming soon with our analyzers. We are a 100% torque focused company, meaning that all we do is related around torque, whether it be calibration or measuring torque or applying torque. That is our focus as it relates to manufacturing. We have customers throughout the medical field, biotech, aerospace, the military, automotive, and also electronics as well. And so let's go ahead and jump into what we're going to be talking about today, and that's how we can get started with the fastening automation workflow and how a DC tool can help with that process. And when we talk about what is workflow, we all understand that that is a repeatable process that allows us to be able to produce something. In this case, we are talking about producing products and using fastening tools to do that as part of the overall workflow. And when we look at what different types of workflows are in the industry, a lot of what we get and we see is from lean manufacturing. And so what lean manufacturing tries to do is tries to identify and remove waste from the process. And so there are basically 7 different categories of waste. And if this is something that you're very familiar with, please just delight me for the review for some of those who may not necessarily know what we're talking about. But when it comes to the waste that we're trying to avoid, the first is the waste of transportation, and that deals from when the product is raw material until it is finished, that entire path of that particular product. That can be a waste. Inventory, if we produce too much inventory, that's unused capital, that's not generating any income, we get a waste there. There's the waste of motion, and that primarily deals with people and poor designed workstations and possibly movements. There's also the waste of waiting. And this primarily deals with parts that may be moving down the line that are stuck at one spot or another. and they don't get moved on. And then the opposite of that would kind of be overproduction. We get so much production done in one spot that we do create waiting in other spots. We do have overprocessing waste, and that's where product is maybe handled or touched from the customer's aspect that means nothing to them. And then the big one, the big daddy, is defects. And so if we can avoid defects, that is fantastic, because if we do see a defect, that can certainly impact every single one of the previous wastes that we looked at. And so if a defect happens at the very beginning part of the process, then that is only compounded and is going to cost more money to fix or possibly scrap that particular product. And so the defect can affect, obviously, the transportation, because now that part has to be moved to another location. You have waiting for the part to be reworked. You now have inventory that is not being used, capital that is not generating any income. And then again, we have over processing, because this step really adds no value to the customer. And then that product then, or material, is overproduced in that general form. So the defect can really play a big part in the amount of waste that could be generated from the lean manufacturing side. And so these different categories were all kind of classified and put together by Ono, the Japanese gentleman, part of the Toyota production system. And so these were identified and classified as Mura, and that is the Japanese word for wasteful. And so when we look at this in its entirety and kind of what the other components of this are, there are two very important components then, other than just looking for the waste and trying to eliminate it. And those other two terms are Mura and Murai. And so if we look at Murai, that is basically means overburdened or overworked. And so this can relate to either personnel, operators. It could mean also for machinery. And this is the part of the process where we get so much output that needs to be generated that we're putting a strain on the operator, or we're putting a strain on the equipment that we're using to try to meet the demand that is being asked. And so that overburden or overworked can lead to, again, additional waste, because maybe mistakes aren't as noticeable, or because of the amount of work that's happening, the operator passes over it, or it just moves by them. So this particular part is a really key component to the overall total workflow. The other component is the Mura, and that basically means uneven or unbalanced. And this can primarily be seen if we look at this graphically. So with a, basically the dotted line there is the capacity of the manufacturing process throughout the life of the product that's being manufactured. And so we see the low areas are possibly waiting, and then the high areas there, or the hills and valleys, those mean the overburdened portion of the process. And so to kind of highlight that, when we look at the differences We can see that the Mora is the overburden part of that, and the valley there is where waste can happen, and primarily does, again, in the form of weighting, in the form of overprocessing, and some of the other items that we talked about. But if we look at the overall process first, instead of trying to attack the actual waste, and we can help to kind of flatten the curve, as it were, to make the flow more smooth, and obviously get it closer to the dotted line, then some of those wasteful things that we see in the Muda will take care of themselves. So if we don't have parts that need to be, that aren't waiting, then we've eliminated that because the flow of the parts are going through and working correctly. So if we can identify the certain high points and low points of the production process and look to solve those first, then the waste component in some instances will take care of itself, but it will not take care of it completely. So you've got to be on the lookout for those particular items of waste if we are dealing with the lean manufacturing principles. And so now we're going to have our poll question right now. So in your process, are there fastening or multiple fastening steps that may be providing waste to you at this juncture? So we'll give you a few minutes here to go ahead and answer the question. All right, we have the results coming in, and it is looking neck and neck, pretty much 50-50. So we do have some people within the conversation here that do feel that part of their fastening processes can be producing some type of waste within their particular workflow. And so let's go ahead and we're going to try and take a look at how, how the DC tool can help assist with the workflow as it relates to fastening. One of the great things about the DC control tool is how much control we have of the rundown from once the trigger is pulled until the operation has been completed. And so what we're going to do is, or if we take a look at the overall structure of a DC tool, we do have the ability to have multiple preset profiles. So we can consolidate operations. So if you do have pneumatic clutch type tools or electric clutch tools set up at different workstations, and you want to kind of consolidate that work, giving you the ability to reduce the amount of functioning work as it relates to motion and things of that nature. This is a good way for us to be able to do that by the use of multiple presets. And so that's going to, again, that's going to help with the motion and the transportation aspect of the waste, because we have the product in one location longer, doing the steps that would take place further down. So we're eliminating that portion of waste. Again, we were eliminating some of the weighting that can happen as the product moves down, and it may again get get bogged down at a certain point, and if we can eliminate that, then that's going to help the flow as well. And then there's going to be some other some benefits as well. We will be able to have some increased production. We'll also be able to reallocate resources. So if we do have different workstations that have been consolidated, and we can move those to another part of the process that may deal with another area or another department, then you also have that ability to do that same type of thing with personnel. So we're not going to need as many operators to do the same type of processes through the use of the consolidation. So that gives us, again, the ability to use the different presets to be able to consolidate and be able to tighten up the flow process to eliminate some of the waste items that could potentially be there. Another thing that the DC tool can certainly help with is overprocessing. And so with the ability for the tool itself to be able to have error proofing abilities within that, that gives us the ability to further down the line to eliminate any type of maybe inspection that may need to be done. Because if we can error proof that particular fastener at the moment when it's installed, and we know that it is to the correct torque, the correct specification, we can help to eliminate the overprocessing waste that we may see with that. And with that information, we can also get the torque data that would be associated with that particular rundown. That data for our systems can be stored either on the controller itself. It can be streamed out via the RS-232 or Ethernet port. And we do have that ability to keep and store that data to be collected and then collated and used for either analysis or documentation of the process when it was done. So all kind of encompassing within that whole type of error proofing and data collection, we can kind of wrap that all up into a process control for a specific cell or assembly build, where we can use different presets, and we can automate how the tool is being used to automatically move from one preset to another based on the amount of good fasteners that we have for a specific assembly. And we're going to do this process within the demonstration part of the presentation. And so we'll have all of that kind of wrapped up into the process control portion, and you'll be able to see what that looks like. Along these same lines, we can certainly help to eliminate the big one, and that's the defects. And so it's going to be the exact, primarily the same as it would be for the overprocessing. And so we can, let's just move this over here. So we can, again, we can error proof that assembly process. We can capture and collect the torque data that happens. And we can also put all of that wrapped up in process control. So the operator can do their repetitive work, making sure that the workflow and the amount of throughput that comes through is done at the right time for the right amount of time, and we can move the product through the entire flow of that assembly build. And so again, if we can handle and help to eliminate the fastening defects, that's certainly going to help eliminate a lot of the waste that we could see as I mentioned earlier, as it relates to the defects being able to contribute to just about every single other waste form that we do see. So let's go ahead and take a look at the fastening process itself. And then we'll look at some scenarios on how we can implement some of these methods to help combat against some of the waste that we may see in the fastening process. And so I'll put up on the screen here basically a graphical representation of what will happen during a rundown that may take place with a particular fastener. So what we'll see is at the very beginning of the rundown with our time versus torque, we'll have the beginning, then we'll have basically the thread engagement process, which in most cases is not going to be producing much torque at all. Then we're going to come to a point when the surfaces come together and mate, and then we're going to see our rise in our torque value, and then the tool is going to shut off once it reaches its particular torque value. And so if we look at what that looks like in the tool itself, so let me go ahead and I will have our software hooked up to the controller here, and then I have the thread block kind of to simulate the fastening process, so we can kind of look at the different aspects of the scenario that we're going to run through. And so this is the so what you are seeing now is our software that is hooked to the controller. In our monitoring tab under the graph function, this gives us the ability to actually graph the rundown that we're going to do in our application scenario. Now, our system does allow us to have what is an automatic RPM set for a specific torque value. And the lower torque we go, the slower the tool will run. And that's basically allows us to be as accurate as possible when it comes to lower torque values, because we don't want to introduce any inconsistencies with a high RPM tool shutting off at the lower torque and giving us a wide variance of torques. So let's go ahead and run this down, and this will help us with our first scenario that we'll be dealing with. Okay, so you can see that this graph mimics what we just looked at. So we have on the top up here in the red is our speed, and down below here is our torque values. Now, let's go ahead and take a look at the different wastes that we can apply to this particular application. So the application scenario is first Mora, which is overburdened. And because of this taking almost 6 seconds for this particular fastener to run down, actually over 6 seconds, this part of the process is becoming a bottleneck, and we are trying to get through this section of assembly as quickly as possible. And so for us to be able to do this, we have in our programming, we can go ahead and we can use what is called our free speed and free angle. And what that does, it allows us to be able to run the fastener down during the thread engagement portion at a really high RPM. Then it will slow down just before it seats, and giving us the correct RPM that we need for that specific torque value. And so we can do this in our fastening parameter. we'll set our RPM at 600, and we'll set our free angle to 3,500, because this fastener takes approximately 4,000 degrees of rotation to run down. So now that we have added that, we can come back out, and let's go ahead and run that down. Now we can see that that has dramatically decreased the amount of time it took for that particular rundown. And that was just under 1 second, or just at 1 second for us to be able to do that. So in this case, we shaved over 5 seconds for this particular rundown, as well as keeping it within the torque specification and the RPM for this suggested torque value. And so that particular scenario there is solved. We've done that. So now let's look at our next thing that we want to look at, and that is how we can remove waste from defects. And in this case, we may see some cross-threading that happens on this particular fastener. And for us to be able to deal with that, we can use what's called our free reverse at the very beginning of the rundown, where we can start the tool in the reverse direction, and then at a very slow RPM, let the threads find the correct spot, and then run the tool in its forward direction. And for us to do that, we can just go back into our menu under parameter, and in our advanced tab, we have our free reverse. We can set that RPM speed to say 75, and we'll set the amount of turns to a half a turn. And now when we come back out to run this, it will start in that reverse rotation, find a thread, and then begin the tightening process. So let's go ahead and do that. All right. Now, again, this is going to help us with that cross thread detection. And now we've helped to eliminate that particular defect within the waste that we might see. The next waste that we want to try to look at again is another defect, and we can control this by error proofing. So we want to make sure that the operator is using the correct fastener in the correct location for that particular operation. And for us to be able to do that, we can not only set our torque value that we have here, but we can also set an angle requirement for that particular fastener. And in this case, we know that our fastener is roughly takes around 4,000 degrees of rotation for it to fully seat. So let's go ahead and we can create a window to make sure that when the torque value is reached, that it has met a certain amount of angle. And for us to be able to do that, we can go back into our parameter menu in the fastening, and we can enter in our minimum target angle and a maximum angle. So let's go ahead and do that. We can set our maximum, let's say it's 4,400 degrees of rotation, and then our minimum is going to be 3,800 degrees of rotation. And now we can come back out and run this down. Okay, and so you can see here that our total amount of angle was 4,100 degrees or so. So it met within that particular angle window. Now, if we were to use a different fastener, let's go ahead and use this scenario here. We would receive an error because of the fact we didn't meet the angle and our torque actually was out of the acceptable limit as well. So in both cases, we've essentially error-proofed this particular fastener by ensuring that not only the torque is met, but a certain amount of angle is met as well. So this can be helpful if there is a washer series or a washer stack that needs to be included in the fastening. And if that is not there, then that is going to have us an angle displacement difference, and we would be able to detect that particular error. So defects with error proofing is solved. Next is going to be our overprocessing or inspection, and we can use basically the same error proofing setup to allow us to maybe eliminate some inspection of a certain fastener that may be causing issues. So with that, we can also solve that part of the waste that we may see from overprocessing. Because of the fact that we're error proofing, we have the opportunity to reduce the amount of inspection. And lastly, we can look at overprocessing. And so with the ability for us to do data collection with the error proofing, this will allow us to be able to look at certain fastening processes as they have happened, and we can go back and take a look at that. So with that, that has been solved as well. Chris, any questions at this point? I can see.
Yeah, Dave, we have a few questions to ask you.
All right.
First one is, what is the value of programming an angle rotation, and is there a typical application for it to be used in?
So the system itself, when we're using it with torque control and the angle monitoring, that gives us, again, the ability to make sure that the fastener has been seated properly. We do have that ability to kind of do the reverse, where we can just turn the fastener to a certain degree, and then we can also monitor the torque. So we can kind of use both of those in different presets to help manage and achieve different results. But the main thing for us to be able to see with the angle monitoring is to make sure we don't miss or we don't incur defects like cross threading, which would certainly hit the torque value that we would see, but it would happen right at the very beginning of the rundown. So if the operator is not paying attention, or if we don't have angle, they may run a cross thread fastener and just feel the tool go ahead and shut off, and then move on to the next fastener, and then that fastener was never fully torqued or seated. So the angle monitoring does help to eliminate that part, that defect. It can also help, again, where we're monitoring the amount of turn. So if there are washers or a series of washers or a washer stack, some other type of group within the fastener that's going to change the amount of angle that we may see, that will alert us as well that those particular washer stack was not included in that assembly, and we would receive an error, and then the operator would then have to reattempt that. And then if we're using the process control, they wouldn't be able to satisfy the requirement of a good rundown until they finished achieving a good rundown for that specific value.
Okay, thank you. Next question is, for a fastening application that uses like a delicate part, like say a plastic piece, how much control of the rotational speed can you control for the initial rundown so you don't melt the plastic or strip it?
So we can set the RPM anywhere up and down the available requirements of the tool. So if you want to have a very slow RPM, we can set that to be extremely slow, or we can have it do as I did with the example. Hopefully you saw it, where it can run at a really fast RPM during the thread engagement process, and then slow down for the final and seating torque to make sure we don't overshoot the torque value. So the RPM can be programmed to whatever value makes sense for your application.
Okay, thanks. Next question. Can a barcode label be placed on a component and scanned to trigger a pre-programmed fastening event?
Yes, we can certainly use a barcode scanner to pull up a specific preset for a specific group or uh, an assembly process or just a simple preset. Um, so a barcode scanner can be used for that. We can also use the digital inputs and outputs that we have available with the system to where we can have a PLC be able to send a signal to the controller to tell it to which preset it needs to use for that um, particular part. So if there is some variation in the product builds, and if there is more mix, we can certainly help to accommodate that by having additional input devices be able to select certain programs and presets for that specific part.
Okay, thanks. Looks like last question is, can a program fastening sequence be integrated into like an external line control sensor to release the product once the entire fastening sequence is completed?
It certainly can within the model process or the assembly. We can include inputs and outputs. So signals can be sent in or it could be sent out at any point through the assembly. So for example, if we had a part where there was uh, fasteners that are going to be put on one side and they also need to be put on to the other side, but we need to remove the part from its jig, rotate it, and then lock it back down. We can accomplish that with the use of the inputs and the outputs. So after the first set of fastening is done, we can send a signal out to the locks to release. Then the operator can go ahead and adjust the part, put that back in, go ahead and lock it. And then once the system sees that it has been locked, it will then go ahead and move to the next step for that particular fastening of the remaining fasteners for that part. So that can be done. We can certainly send signals out once the entire cycle has been completed. So there are a lot of different things that we can include within the model or process control component that is in the EC and the ECT tools.
All right, thanks, Dave. And that was the end of the questions.
All right. Again, thanks very much for joining us today. I do apologize if the viewing was a little bit wonky during the demonstration portion of it. But again, if you'd like to see something that would be a little bit more tailored to your specific application, feel free to reach out to us either through the chat. You can also reach us through chatting directly on our website, or you can call us. You can email us. You can reach us through our various social channels as well. So there are a number of different ways that you can contact us, and hopefully we can help you and help to provide a demonstration that may be a little bit more tailored to your specific need to help you reduce your waste. That didn't sound great, but and help with your workflow and how the DC tool can help with that. So thanks very much again for joining us, and we'll see you next month.